My name is Muchová, and in my talk I would like to speak about theoretical modeling of X-ray processes and how this modeling can be used to understand the structure of aqueous solutions. Our research is motivated by the novel experiments in the X-ray domain. These experiments are connected to the recent development of new facilities, such as synchrotrons or free electron lasers. These facilities are producing ultra-short and intense X-rays, and they allow us to perform unprecedented experiments. In these experiments, the structures of unknown or transient species can be determined, or we can investigate the structure of proteins in actions, and it can also give us the ideas about the electron density changes during the chemical reactions. In our work, we are studying the interaction between the hard X-rays and matter. We are studying the liquid solutions of ions, and we are trying to understand and interpret the reaction mechanisms which are triggered by hard X-rays. Because this field is rather underdeveloped from the theoretical perspective, we are also creating and collecting the theoretical tools to allow us to understand and model all of the processes as a whole. Why it's important to study the interactions of X-rays and ionic solutions? It's important because of the general interest and unknown features of the interaction, but it's also connected to the X-ray damage to biomolecules. As we know from the previous studies, the X-ray damage to biomolecules can be either direct, therefore the biomolecule is destructed directly by the intense radiation, or it can be indirect by a transient species which are very reactive. This can be, for example, water radical, which is created from irradiated water. Therefore, if we understand well the X-ray processes which are triggered by the radiation, we can understand also the details of the biological damage. In our work, we are trying to interpret the experiments performed in the liquid microjets. These experiments are done in Berlin by Dr. Winter, and these experiments are the radiation in, electron out type of experiments. They are based on the photoelectric effect. Therefore, when the sample is irradiated by X-rays, the radiation causes ionization of the molecules, and the energy of the outgoing electron is measured. These are the so-called primary electrons, and it's a photoelectron spectroscopy. However, the strong X-ray can also lead to ultra-fast decay processes in the ionized molecules. In this case, there are the so-called secondary electrons created. The energy of this secondary electron is very different than to the energy of the primary electrons, because these are very slow and can be very destructive. This type of spectroscopy is called the Auger electron spectroscopy, and these two spectroscopies are giving us different information which is in a way complementary about the electronic structure and also the structure of solutions. So if we understand both the primary and secondary electrons and can model all of the processes which are leading to the ejection of these electrons, we would be able to understand how ions and water influence each other. In other words, what is the electronic structure of the solutions. We would be also able to model the chemical environment, the neighboring molecules, and we would be able to adjust the ion pairing patterns in solution, which is otherwise experimentally very hard to understand, or it's very hard to access. And we would also understand what is the direct mechanism by which the molecules are getting rid of the excess energy. And if we understand these processes, we would be also able to affect it and control it. In my talk, I would like to devote specifically to aluminium chloride, which is a very interesting molecule from different perspectives. As we know, the ions are not placed randomly in solution, but they form some sort of ionic pairs. Aluminium chloride is very specific because it forms coordination bonds with its neighbors. However, there is a wide variety of possible structures of aluminium chloride in solution. Either there can be only water molecules in the coordination shell, or there can be chloride molecule, which is neighboring to aluminium chloride, aluminium cation. As we know from the experiments and also from the basic chemical knowledge, aluminium also undergoes hydrolysis. Therefore, there can be hydroxyl anion also in the coordination sphere. And unfortunately, this type of complexes also form dimeric and trimeric structures. So the speciation of aluminium in solution is very wide, and we were especially interested if we can use the X-rays to determine the structure of the aluminium complexes in solution. To understand what are the most common structures in a solution of aluminium chloride, I did several types of molecular dynamics simulations. I performed the simulations in a large box. I also performed ab initio molecular dynamics for a smaller system or even for the systems in clusters to understand what are the average distances between aluminium cation and its neighbors, and also to get the understanding what is about the role of the environment. From the molecular dynamics simulations, I've learned a lot about the structure of the solution. I also have to say that a special attention must be paid to the types of molecular dynamics which are performed to study the structures, because there can be a very large discrepancy between the classical or ab initio structures. What I have studied, what I have learned from the simulation is that the chloride atom is typically not in the coordination shell, and if it's present, it most probably helps the hydrolysis. When I placed the hydroxyl group into the coordination shell directly, I observed the formation of the Zondel-like structures. Therefore, the hydroxyl is bound to the water in the second solvation shell, and from all of this I can conclude that the most typical structure of aluminium chloride in solution is aluminium hydroxy aqua complex. Therefore, I have the most common structure, and I need to perform ab initio calculations to be able to adjust all of the peaks which are measured in the experiments and which correspond to both primary and secondary electrons which are going out from the solution. If I want to perform the ab initio calculations well, so that I can address all of the peaks which were measured, I need to accurately describe the environment. As I mentioned before, the experiments are measured in solution, so the polarization of the solution must be modeled accurately. In this case, it's even more complicated because the experiments are performed in concentrated solutions, and a simple polarizable continuum model is not accurate in this case. To be able to understand the energetics, that means that the position of the measured peaks, we have to accurately calculate the energy, so the core, inner valence and also valence electrons. Therefore, we have to correctly address the energy of the initial states, but also of the final states, which contain two holes. To model the whole spectra, of course, we would like to model the intensities of the peak, and in principle, it's also important to model the outgoing electron. However, modeling of the outgoing electron requires a special theoretical treatment based on the final theory, so for the moment we can forget about the outgoing electron. To model correctly the effect of the environment and the polarization of the aqueous solutions, I used the project ChemFels to travel to the University of Pisa and to join Benedetta Menucci's group in the university. Their expertise lies in the accurate description of the environment through the polarizable electrostatic embedding models. So I I studied there the effects of the polarizable environment on our quantum system, and I learned how to perform the simulation in this complex environment. In these simulations, we divided the system into the quantum part and into the part, in which the electrostatic interactions are modeled based on the multiple expansion of the interactions. This force field is very accurate and also can provide an advantage to continuum models, because it can also include the effects of ions, which is otherwise impossible to model in continuum models. I performed many simulations with this force field to test the applicability for our problems, and I can conclude that this QM-MM arrangement, this QM-MM embedding polarizable, properly describes the specific and bulk effects both in the ground and also in the ionized state, and can be used with advantage for our type of simulations. In the next step, we need to access the energies of the core inner valence and valence electrons to model the spectra. Typically, we are using two approaches. One is for modeling of the whole spectra, but it's mainly useful for modeling of the valence electrons. This is based on theoretical trick, how we can model the ionization. We can model it as an excitation to a distant center via the restricted orbital space TDDFT. This has an advantage that all of the ionizations are treated on equal footing. Therefore, we can get the accurate energetics of all possible transitions. It allows us also for modeling of the whole spectra, also with the intensities and the width. However, to study the absolute positions of the core ionized states, this approach is not useful. Therefore, for that we use an algorithm trick to the SCF convergence protocol, which is called the maximum overlap method. In the traditional SCF convergence SCF protocol, we are looking for the orbital coefficients for the occupied orbitals that are those that minimize the total energy of the system. However, in the maximum overlap method, we are modifying the algorithm to find the new occupied orbitals as those that overlap most with the occupied orbitals from the previous step. Therefore, if we create the initial wave function with the core hole, we are optimizing the new occupied orbitals in a way that it conserves the core ionized state. The advantage is that this maximum overlap wave function can be a good starting point for post-Hartree-Fock methods, which means that we can get very accurate energetics of the core ionized or inner ionized states. And it can be also coupled to the polarizable force field. If we want to access the energies of the final states, that means that we would like to localize the second hole from the secondary ejected electron. We are combining the maximum overlap method again with the polarizable amoeba force field. This approach allows us to localize the two holes either on previously ionized atoms or on the ionized atom and its neighbor, or the holes can be also localized on two neighbors. This method has an advantage that we can localize the charge into separate units. This problem is very difficult to handle theoretically because the standard quantum chemical method converged to the lowest energy solution. However, combining the maximum overlap method with polarizable amoeba force field, we are able to access the accurate energetics of even of these states. So at the moment, I'm trying to interpret the measured spectra of the final states and also of the initial states. As I mentioned before, the neighbors of the irradiated aluminium cation are mostly water molecules. So I'm modeling the energies of the final states, and we are trying also to access the intensities of the peaks that were measured experimentally. The research is still undergoing because there are large discrepancies in the energies which are corresponding to each of the states. And we are also facing the problems connected to the overlapping of the signals coming from the chloride and of the hydroxyl anions. Therefore, it complicates our possibilities to distinguish the peaks which are in the same region. Finally, I would like to thank to my colleagues in Prague, which helped me with the development of methods for X-ray spectroscopies, but also to the group of Benedetta Minucci in Pisa, where I have learned how to use the polarizable force field and how to model the reactions in solution. Finally, I would like to thank to the project which helped me to support my stay in Pisa, and thank you for your attention.